The Earth is essential for the planetary group. Also, the nearby planet group is essential for the smooth way. Yet how does our home world, as a matter of fact, fit into the bigger construction of the universe? Well, truth be told, our cosmic home isn't a recluse either, but is instead an essential piece of a much bigger construction that draws innumerable system groups into its circle with its enormous gravitational shaft. However, this is exactly where it gets precarious. While cosmologists have long expected that our grandiose home belongs to the Lanark supercluster, an astounding discovery now suggests that we have been arranging the smooth way completely off base. Rather, the new data suggests that we are, in fact, subject to the influence of a much more imposing attractor, one that has the second largest gravitational well in the nearby universe, and that is slowly pulling us closer and closer to itself. Albert Einstein had a clear idea of the hidden designs in the cycles of the universe after the approach of quantum mechanics in the 1920s, which couldn't precisely predict where a molecule would be at a given time or whether it would even still be a molecule at all. Einstein wrote the following lines to his friend and physicist Max Born: "The theory gives a lot, but it doesn't bring us any closer to the secret of the old one, that is, God. Anyway, I'm convinced that he doesn't play dice." The creator of the theory of relativity was, therefore, persuaded until his death in 1955 that the universe functions according to the fixed principle of cause and effect, that it operates by explicit laws, and that the ancient one leaves nothing to chance. And if we move this principle from the discussion of quantum mechanics to the cosmic scene, we recognize that the heavenly dice can indeed stay in their cup. In this case, after all, galaxies and galaxy groups do not move randomly and arbitrarily through space. Instead, they are all firmly connected to invisible flows, directed by large-scale differences in the density of matter. And if you like, the designs of the universe, in their intelligible star grouping, resemble a kind of settled, larger-than-average Russian doll. While the Earth is known to belong to the nearby planet group, the planetary system in turn belongs to the smooth way. And despite the fact that our home galaxy, with its diameter of 100,000 light-years and its roughly 200 billion stars, can be described as impressive, no doubt, we should not forget that in the grand picture, it is only one of countless unique pieces. In fact, the smooth way is an important part of the so-called local group, and thus of a galaxy group that is home to around 30 obvious and 70 known dwarf galaxies. The local group, in turn, is part of the Virgo supercluster, which contains about 100 to 200 galaxy groups and is itself part of the Lanark supergroup. While this giant uberstructure has a diameter of 520 million light-years and contains around 100,000 galaxies, it also acts as an attractor, much like the Shapley supercluster or the Sloan Great Wall. So we're dealing with huge gravity wells that draw galaxies and galaxy groups to them over a wide region. Anyway, there are also, in fact, structures in the immensity of space that display a totally different characteristic. After all, the universe's pore voids or the dipole repeller are better known for pushing the cosmic affiliations away from them. But back to the sheer power sinks for a better illustration. The researchers compare their impact with the earthly river systems. Just as the natural terrain decides the course of the water, the bend of space through attractors also decides the movements of celestial structures. So, while this is all theoretical, which attractors have really extended their gravitational grasp on the smooth way in practice? The gravitational megastructures of the local universe. Well, that is precisely the question. And really, we thought we had long since found the answer to it. According to a study, previously considering 8,000 galaxies, our cosmic home is clearly located in the Lanark supercluster. But, as often happens with galactic discoveries, they are only considered certain until they are questioned again. And that is precisely what the researchers, led by Alien Valid from the University of Marseille and the Leibniz Institute for Astronomy in Poitiers, have now done with their cosmic test. The scientists used the databases of the Cosmic Flows 4 survey, which this time included not just the position and movement of 8,000, but of around 56,000 worlds with a span of 1 billion light-years. But how do you, indeed, even sort out such an enormous smorgasbord of data into a subordinate setting? Great question. The primary task for the astronomers was to reveal the legitimate movements of the individual galaxies based on extraordinary calculations in view of cosmological parameters. They then looked for fixed designs that gave hints to the location and catchment area of the giant attractors. Thus, the researchers were able to determine not just the likelihood of the presence of such an attractor, but also whether a specific point in space was connected to it, and where the new data treasure was multiple times larger than the previous one. There was, at last, a comprehensive 3D model that described the flows and large-scale gravitational structures of the nearby universe in a degree of detail that had never been achieved before. In particular, the boundaries between the individual ranges of authority of the attractors could be mapped more precisely than ever before. Here is the passage with proper punctuation. The analysts had the option to distinguish 17 huge gravitational wells in our enormous neighborhood along these lines, and one of them stood apart from the rest, the Sloan Great Wall, along with its related structures. It is the gravitational giant in the neighborhood universe, and that is implied clearly, with a length of something like 1.37 billion light-years. The massive system wall is none other than the largest known touching structure in the whole universe, and through its massive construction, the huge catchment region of the Sloan Great Wall thus envelopes a portion of 1 billion cubic light-years. This means that its gravitational well is about twice as large as that of the next biggest attractor, the supposed Shapley supercluster. Yet, the full story also includes the way that the gravitational degree of the two giants could ultimately be much greater later. All within the model, they are restricted by the outer edge of the data field. In light of this, specialists estimate that in reality, the gravitational bowls extend much farther than on paper. But where does the Milky Way fit into the image of these enormous cosmic structures? As mentioned, our home system was previously thought to be part of the Laniakea supercluster. However, the latest analysis now greatly challenges this classification. Have we misidentified our home galaxy? According to cosmologists, the stream related to the Milky Way is heading toward two different gravitational wells. The favored endpoint isn't the Laniakea supercluster as previously accepted, but the Shapley supercluster. This applies to nearly 60% of the galaxies analyzed, while only around 40% are thus moving toward the Laniakea supercluster. Alternatively, this new finding could now mean that our Milky Way doesn't belong to Laniakea at all, but to Shapley. However, maybe this eventually applies not only to the local group, but also to other parts of the Laniakea supercluster, which we have up until now misclassified. But why is this significant from a galactic perspective? Why does it matter that we may now need to find our galactic home elsewhere in space? Well, such a cosmic migration really does hold tremendous potential for researchers. After all, the effect of the latest study gives scientists completely new insights into the gravitational landscape of the nearby universe. Specifically, the findings show how galaxies and other structures interact with one another over time and what factors influence them. Applied to a broader context, this might actually help researchers better understand the similarly tangled and complex dynamics of the universe and its distribution of matter more clearly than ever before. Whether we will also succeed in understanding the origin of the enigmatic dark flow more precisely than ever is another matter altogether. There is one thing we must not neglect. Although structures like the Sloan Great Wall or the Shapley supercluster, with their vastness, already test our imagination, it may be the case that much more gigantic structures are hiding out there. A couple of years ago, a NASA working group led by Alexander Kashlinsky discovered that 1,400 galaxy clusters follow an oddly uniform stream that must be caused by a supergravitational attraction. However, since its source clearly lies beyond the perceptible universe, we can't exactly say what kind of entity we are dealing with here. Despite the analysis of his colleagues, Kashlinsky continues to hold onto the possibility that the measurements are not a statistical fluke. Still, without hard facts, he too can only speculate about the true nature of the dark flow. In this regard, he states, we need more data to see what it is or to narrow it down. The main point we can make with confidence is that somewhere far away, the universe is altogether different from what we see locally. Whether it's an alternate universe or a different space-time continuum, we don't know. But we do understand what we need to do. Press the like and subscribe button now so you never miss another video from us again. We'll see you soon.